Hello, in this lecture we'll find out the length of line segment AE. In the drawing we have rectangle ABCD. We know that side AD of this rectangle ABCD equals to 3 units in its length. In addition, inside this rectangle we have those two semicircles. The radius of this big semicircle equals to 2 units. The radius of this small semicircle equals to 1 unit. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside any rectangle are right angles. So those 4 angles, they're all right angles. So this is a right angle. This is angle ADC, that is also a right angle. This is angle BCD, that is a right angle. Finally, this angle CBA, it is also a right angle. In the next step, we'll define the relevant points to this question with letters. We'll define the center of this semicircle, this point is point P. We'll define the center of this small semicircle, this point is point Q. We'll define the touching point of those two semicircles, this point is point S. We'll define the point of tendency of tangent AE with this big semicircle, this point is point L. And finally, we'll define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we'll do a construction, that is to say, we'll extend line segment AE and side DC by a straight line until they touch each other. Okay, this point is their touching point. We define their touching point as point F. Side DC is one side of this rectangle ABCD, and therefore it is absolutely a straight line. Then we extended the straight line DC by a straight line, and the result is DF. When you extend the straight line by a straight line, the result must be a straight line. Therefore, DF must be a straight line. So if we focus on the upper side of this straight line DF at point C here, the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So we have here triangle, the small right triangle ECF. We define this angle EFC as alpha. So in the small right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third BC angle must be equal to 90 degrees minus alpha. According to the sum rule, that the sum of the angles in the triangle is equal to 180 degrees. We have here, this is PL. PL is the radius of this big semicircle that is equal to 2 units in its length. The radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. So here we can implement rule 1. I repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we also have here tangent AB is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And in addition, we have also in the drawing line segment OM. OM is the radius of this circle that is equals to R. The radius OM is on to point M, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is on to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius BL that is equals to 2. The radius BL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG that is equal to 1. The radius QG is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever we have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So in this small right angle QGF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third BC angle must be equal to 90 degrees minus alpha. So write it down. This angle equals to 90 degrees minus alpha. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, therefore this third BC angle must be equal to 90 degrees minus alpha according to the same rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the right big triangle LPF is similar to the right small triangle GQF. So I write it down. We prove that the right big triangle LPF is similar to the right small triangle, GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle PLF. In the right big triangle LPF, it is equal to this angle, that's actually angle QGF. In the right small triangle, FGQ. Repeat again. Actually found out that angle PLF in the big right triangle LPF equals to angle QGF in the small right triangle FGQ. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha, as it is belongs to the big right triangle PLF, it will be defined as angle LFP. Angle LFP, and angle alpha equals to itself. So if we relate to angle alpha as it is belongs to the small right triangle ECF, it will be defined as angle EFC. Repeat again. This equation means that angle alpha equals to itself. We just called to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle LPF. In the big right triangle PLF, and it is equal to this angle, that's actually angle GQF. In the small right triangle GFQ. Repeat again. Angle LPF in the big right triangle PLF equals to angle GQF in the small right triangle FGQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I actually proved that all the triangles inside the big right triangle LPF are correspondingly equal to all the triangles inside the small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it now. I actually found out that the big right triangle LPF is similar, this is the sign of similar, to the right small triangle GQF according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LP, the big right triangle LPF, over side GQ in the small right triangle GFQ, equals to side PF in the big right triangle LFP, over side QF in the small right triangle QF GFQ. So I'll repeat again. We will derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP is the radius of the big semicircle, that is 2 over GQ. GQ is the radius of the small semicircle, that is 1, and it is equals to PF. What is the length of PF? First of all, we know that DP equals to PS, the above the radii of the circle, that is equals to 2. So I write it down. Know that DP equals to 2, and PS is also equals to 2. The above the radii of this semicircle, that is equals to 2. Likewise, we have QS equals to QC, the above the radii of this small semicircle, that is equals to 1. So QS equals to 1, QC also equals to 1, and finally CF is the missing side, so we define CF as X. CF equals to X according to our definition. So in total, we have found out that PF equals to 2 plus 1 plus 1, that is 4, plus X. Repeat again, PF in total equals to 2 plus 1 plus 1, that is 4, plus X. So PF in total equals to 4 plus X. Over QF. QF in total equals to 1 plus X. Again, QF in total equals to 1 plus X. So in conclusion, I have found out that 2 equals to 4 plus X over 1 plus X. Here we'll multiply this equation by 1 plus X, and we get that 2 times 1 plus X equals to 4 plus X. Here we'll open the brackets on this side of the equation, and we get that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtract x from this equation, and you get that 2x minus x is x. Therefore, this side of the equation we left only with 2 plus x equals to 4. Here we subtract 2 from this equation, and finally get that x equals to 4 minus 2, that is 2. So x equals to 2 units in its length. So line segment CF, that is equals to x, is equals to 2 units. So I write it down. CF equals to x equals to 2. In the next step, we will prove that the biggest right triangle in this drawing, that is triangle, the right triangle ADF, is similar to the smallest right triangle, in this drawing, that is triangle ECF. Repeat again, we prove that the big right triangle ADF is similar to the small right triangle ECF. So I write it down. We prove that the big right triangle ADF is similar to the small right triangle ECF. So why the big right triangle ADF is similar to the small right triangle ECF? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So this is actually angle ADF, in the right big triangle ADF, and it is equal to this angle, that is actually angle ECF, in the small right triangle EFC. So I repeat again, I actually found out that angle ADF in the big right triangle ADF equals to angle ECF in the small right triangle EFC. They are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both angles. So we can write down that angle alpha equals to itself is a common angle that belongs to both angles. So if we relate to this angle, angle alpha, as it belongs to the big right triangle ADF, it will be defined as angle AFD. And angle alpha equals to itself. So if we relate to this angle alpha, as it belongs to the small triangle EFC, it will be defined as angle EFC. Okay, again, this equation means that angle alpha equals to itself. We just called to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both angles. And finally, those two angles, they are both equal to 90 degrees from alpha, therefore they are equal to each other. So finally, this is angle FAD. In the big right triangle ADF, and it is equal to this angle, that is actual angle FEC. In the small right triangle EFC. So I repeat again, actually found out that angle FAD, the big right triangle FD, equals to angle FEC in the small right triangle ECF. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the triangles in this big right triangle ADF are correspondingly equal to all the triangles in this small triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. So we found out that the big right triangle ADF is similar, this is the sign of similar, to the small right triangle ECF according to angle similarity rule. And from the fact that the big right triangle ADF is similar to the small right triangle ECF, we will derive that the following relationship exists between their sides. We will derive that side AD, the big right triangle ADF, over side EC in the small right triangle EFC equals to side DF in the big right triangle ADF over side CF in the small right triangle EFC. So repeat again. We will derive that side AD, the big triangle, over side DC in the small triangle equals to side DF in the big triangle over side CF in the small triangle. AD equals to 3 according to what is given as the question. So it is 3 over EC. EC is the missing side, so we leave it as it is. And it is equal to DF. What is the length of DF? DF in total equals to 2 plus 2 plus 2, that is 6, plus 1 plus 1, that is in total 8. Again, in total, DF equals to 8. It is 2 plus 2 plus 2, that is 6, plus 1 plus 1, that is in total 8. So DF equals to 8 over CF. CF equals to 2. So in conclusion, we found out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So in total we shall find out that 3 over EC equals to 4. Here we multiply this equation by EC, and you get that 3 equals to 4 times EC. Here we divide this equation by 4, and finally get that the missing side EC equals to either 3/4 or to 0.75 units in its length. So we shall find out that this missing side EC equals to either 3/4 or 0.75 units. So I write it down. This side EC equals to 0.75 units in its length. What is the length of side BC of rectangle ABCD? We have the rule that says that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC. But AD is 3, therefore BC must be, the opposite side BC must be also equal to 3. So BC, we shall find out that BC equals to 3 units in its length. What is the length of the missing line segment? Line segment BE. What is the length of line segment BE? From the drawing it is very easy to see that BE equals to BC minus EC. Again, BC minus EC equals to BE. So I write it down. We shall find out that BE equals to BC minus EC. So BE in total equals to BC. BC is 3 minus EC. We just right now found out that EC equals to 0.75. So in total BE equals to 3 minus 0.75, that is 2.25. Okay, again we should find out that the missing line segment BE here is equals to 2.25 units. So write it down. BE equals to 2.25 units in its length. So here we have again the rule that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But DC equals to 2 plus 2, that is 4, plus 1 plus 4, plus 1 plus 1, that is in total 6. Again, 2 plus 2 is 4, plus 1 plus 1, in total is 6. So DC equals to 6, and therefore the opposite side AB must be also equal to 6 units in its length. In the next step, I'll copy the right triangle ABE, the right green triangle ABE in a new page, and we'll implement the Pythagoras theorem on this right green triangle ABE. Here, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right green triangle, triangle ABE, that I call it from the original drawing. I repeat again that side AB equals to 6, side B equals to 2.25 units, and the hypotenuse AE is unknown. It is the missing side. So according to the Pythagoras theorem, in this right triangle, triangle ABE, AE square equals to AB square plus BE square. So I write it down. AE square, that is the square of the hypotenuse, must be equal to AB square plus BE square. The hypotenuse AE is the missing side, so we leave it as it is. So it is AE square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 squared, that is 5.0625. So in total we can find out that AE square equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So if we found out that AE square equals to 41.0625, here we'll take a root out of this equation and find again that the missing line segment AE is equals to the square root of 41.0625, that is actually equals to 4.608 units in its length. Repeat again, and this is the answer to the question. We actually found out that the length of this line segment AE is equals to 4.608 units. So in the next step, I will summarize the lecture. In this lecture, we found out the length of this line segment AE. So in the drawing, we have rectangle ABCD. Side AD of this rectangle is equals to 4 units. Inside this rectangle, we have those two semicircles. The radius of the big semicircle, this big semicircle, is equals to 2 units. The radius of this small semicircle is equals to 1 unit. Again, our mission is to find out the length of this line segment AE. So first of all, we know that in any rectangle, all the angles inside any rectangle are right angles. So those 4 angles are all right angles. In the next step, we defined the relevant points to this question with letters. We defined the center of this big semicircle, this point is point P. We defined the center of this small semicircle, this point is point Q. We defined the touching point between those two semicircles, this point is point S. Again, we define the touching point of those two semicircles, this point is point S. We define the point of tendency of tangent AE with this big semicircle, this point is point L, and finally we define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we did a construction. That is to say, we extended line segment AE and also side DC by straight line until they touch each other. This is their touching point. We define their touching point. This point is point F. Actually, we extended side DC by straight line. Side DC is one side of rectangle ABCD, therefore it is absolutely a straight line. Then we extended the straight line DC by straight line, and the result is DF. When you extend the straight line by straight line, the result must be a straight line. Therefore, DF is also a straight line. So if we focus on the upper side of the straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is right angle plus this missing angle. In total, they must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. So inside the small right triangle ECF, we define this angle EFC as alpha. So in the small right triangle EFC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this perpendicular angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this right big triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, therefore this perpendicular angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. So we have here, this is the radius PL of the big semicircle. That is equals to 2. The radius PL is drawn to point L. That is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG of this small semicircle that is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So in this small triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, therefore this perpendicular angle must be equal to 90 degrees plus alpha according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big right triangle PF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this perpendicular angle must be equal to 90 degrees plus alpha according to the same rule. In the next step, I actually proved that the right big triangle PF is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So I can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I actually proved that all the angles of this big right triangle LPF are correspondingly equal to all the angles of this small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side LP in the big right triangle LPF over side GQ, the small right triangle GQF, equals to side PF in the big right triangle LPF over side QF in the small right triangle GQF. So I repeat again. We derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QE in the small, over side QF in the small triangle. I repeat again. We derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. LP is the radius of the big semicircle, that is 2, over GQ. GQ is the radius of the small semicircle, that is 1. And we have PF. PF in total equals to 2 plus 1 plus 1, that is 4, plus x. Again, PF in total equals to 4 plus x over QF. QF in total equals to 1 plus x. So, in total we can find out that 2 over 1 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x, and finally found out that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation, and finally found out that 2 times 1 is 2, so 2 plus 2x equals to 4 plus x. Here we subtract x from this equation, so in this side of the equation we have 2x minus x is x, so in total in this side of the equation we have x plus 2, that is equals to 4. So x plus 2 equals to 4, here we subtract 2 from this equation, and finally found out that x equals to 4 minus 2, that is 2. So here, this is 97 CF, that is equals to x, that is equal to 2. In the next step, we proved that the biggest right triangle in this drawing, that is triangle ADF, is similar to the smallest right triangle in this drawing, that is actually triangle ECF. So why the biggest right triangle ADF is similar to the smallest right triangle ECF? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both angles, so we can find out that angle alpha equals to itself, it's a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the three angles in the big right triangle ADF are correspondingly equal to all the three angles inside the small right triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AD, the big right triangle ADF, over side EC in the small right triangle EFC, equals to side DF in the big right triangle ADF, over side CF in the small right triangle EFC. Repeat again. We will derive that side AD in the big triangle over side EC in the small triangle equals to side DF in the big triangle over side CF in the small triangle. AD is 3, according to what is given as the question, over EC. EC is the missing side, so we leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2 plus 2, that is 6, plus 1 plus 1, that is in total 8. Again, DF in total equals to 2 plus 2 plus 2, that is 6, plus 1 plus 1, that is 8. So DF in total equals to 8 over CF. CF equals to 2. So if we found out that 3 over EC equals to 8 over 2. 8 over 2 is 4, so in total we found out that 3 over EC equals to 4. Here we multiply this equation by EC and we found out that 3 equals to 4 times EC. Here we divided this equation by 4 and we found out that the missing side EC equals to either 3/4 or 0.75. So this is the missing side EC, that is equal to either 3/4 or 0.75. What is the length of side BC of rectangle ABCD? We have the rule that the opposite sides of rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC, but AD is 3, therefore BC must be also equal to 3. Here, BC equals to 3. BC equals to 3. What is the length of the missing line segment? BE. From the drawing it is very easy to see that BE equals to BC minus CC. Again, BE equals to BC minus CC. So BE equals to BC, that is 3, minus EC, that is 0.75. So in total, BE equals to 3 minus 0.75, that is 2.25. I repeat again. We found out actually that the missing line segment BE is 2.25. Now we use again the same rule that the opposite sides of rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. But DC equals to 2 plus 2, that is 4 plus 1 plus 1, that is in total 6. So this in total equals to 6. Therefore the opposite side AB must be also equal to 6. In the next step I copied the right green triangle ABE in a new page, and we implemented the Pythagoras theorem in this right green triangle, triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right green triangle, triangle ABE, that is coming from the original drawing. Side AB equals to 6 units, BE equals to 2.25, and AE is the missing hypotenuse. Now, according to the Pythagoras theorem, the square of the hypotenuse, that is AE square, must be equal to AB square plus BE square. Again, AE square equals to AB square plus BE square. A is the missing side, so we leave it as it is. So AE square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36. plus BE squared. BE is 2.25, therefore BE squared is 2.25 squared, that is 5.0625. So in total we shall find out that AE squared equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So we shall find out that in total AE squared equals to 41.0625. Here we took a root out of this equation and finally found out that the missing 97 AE equals to the square root of 41.0625. The square root of 41.0625 equals to 4.608. We'll repeat again. We shall find out that the length of this 97 AE equals to 4.608 units. Okay, thank you very much.